Okay, so the next little bit is going to be on formal charge. This, of course, is electron bookkeeping. And you sort of have to use this with our Lewis structures. Like, can't accurately do a Lewis structure without um, utilizing formal charge. So, as I said before, formal charge is basically electron bookkeeping, and it's assigning charges to atoms that appear to have either too few or too many bonds compared to its normal sort of state of being. So, for example, we have got nitromethane here. And if we think back to nitrogen and ammonia, typically nitrogen has got 3 bonds and a set of lone pairs. So having 4 bonds is and no lone pairs is different than normal. And if we look at this oxygen here, oxygen typically has 2 bonds and 2 sets of lone pairs. Well, this oxygen here has got 2 bonds, 2 sets of lone pairs, so it looks normal. But this one's got 1 bond and 3 sets of lone pairs. So it appears to have too many lone pairs and too few bonds. And this is where formal charge is going to apply. So formal charge is basically this mathematical formula in which you're comparing the normal valence electrons of an atom to the number of bonding electrons it has divided by 2. And you subtract again the number of non-bonding electrons. So remember, there's 2 electrons in every bond. So the number of bonding electrons divided by 2, this is the same as saying the number of bonds. So when I think of formal charge, it's basically the number of valence electrons that it normally would have minus the number of bonds it currently has and minus the number of non-bonding electrons it currently has. So number of valence electrons of the atom normally, and these two are what's going on right now. Okay, so the next slide, if we look back at nitrogen, nitrogen typically has 5 valence electrons. And now it has got 4 bonds, which equals 8 electrons. Okay, so this formula would then be 5 minus 4. 8 divided by 2 is 4. 5 valence electrons minus 4 bonds. And it's got no lone pairs now. 5 minus 4 is 1, so plus 1. Let me bring back my laser pointer here. Oxygen typically has got 6 valence electrons, but in this case, it's got 2 bonding electrons, or 1 bond, and 6 non-bonding electrons. So oxygen's formal charge is 6 minus 1, 1 bond. 6 minus 1 minus 6, this is now minus 1. So nitrogen would be carrying a formal charge of plus, oxygen would be carrying a formal charge of minus, and overall, the molecule is still neutral because plus and minus equals 0. So nitromethane's Lewis structure, the nitrogen would have a formal charge and the oxygen would have a formal charge, and they'd be opposite. And that would be the correct structure, the Lewis structure of nitromethane. Okay, so the next little bit is basically a summary of carbon, oxygen, and nitrogen. And carbon typically has got 4 bonds, and no lone pairs, and its formal charge is 0. If you remove one of the bonds, and so it's an electron deficient system, it's only got 3 bonds and no lone pairs, it's missing those 2 electrons. And this would have an empty p orbital, and you're going to see in the next section why I've drawn this as a trigonal planar system. These are carbocations, so it's got a positive charge here, positive formal charge, carbocation. Conversely, if you replace one of the bonds with a set of lone pairs, we call these carbanions because it carries a formal charge of minus. So if we're following the formula here, number of valence electrons is typically 4, minus the number of bonds. 4 minus 3 is 1, and you've got 2 electrons here. So 4 minus 3 minus 2 is minus 1. And for the carbocation, 4 minus 3 is plus 1. So I'll have a formal charge of plus. So later on in the class, if you ever see CH3 plus, this means you've got a carbocation. And it's also going to mean that you're going to have an empty p orbital. And if you see carbon with the minus, this means that there's a lone pair there, and that carbon is bearing a negative charge. And so the chemistry of both of these two species is going to be wildly different based upon the fact that one's got a negative charge and one's got a positive charge. If we remember our mantra, negative goes to positive, this negative charge is going to be hunting positive charges. So this would be attacking that if you ever had these two together. Okay, so let's move on to the next for nitrogen. So nitrogen typically has got 3 bonds in a lone pair, and this would have a formal charge of 0. Replace this lone pair with a bond. It's now got 4 bonds. Typically, it's got 5 valence electrons. 5 minus 4 is 1, so it's going to have a formal charge of plus. But if you replace one of these bonds with a lone pair, then you've got 2 bonds and 2 lone pairs. This is going to be a negative charge. So this would be nitrogen, which bears a negative charge. This would be nitrogen, which bears a positive charge. So ammonium, NH4 plus. We would just place little hydrogens here, and you've got ammonium. And that's one of the ways that, one of the little tricks for remembering the formal charges of nitrogen and oxygen and carbon. So this is basically the little table for nitrogen. Let's go on to carbon for a sec, to oxygen for a second. And we're going to see that it's very similar to what we saw with nitrogen. So normally 2 lone pairs and 2 bonds, it's going to have a formal charge of 0. And just think of water here, H2O. H, if you got an HH, water's neutral, formal charge is neutral. Hydronium, H3O plus. In this case here, if each one of these bonds was attached to a hydrogen, this oxygen would be bonded to 3 things, and it would have 1 lone pair. So its formal charge would be 6 minus the 3 bonds. 6 minus 3 is 3. Minus 2 for the lone pairs is going to be plus 1. So the formal charge is plus. H3O plus, formal charge plus. Kind of makes it easier to remember, right? And if this, conversely, if you go over here, an oxygen with 3 sets of lone pairs and 1 bond, think of hydroxide. Hydroxide's got a negative charge, right? If we do the math again, this is going to come out to be minus 1 because you've got 6 valence electrons. 6 minus 1 is 5, and then 6 electrons, 5 minus 6 more, minus 1. So if we go back to the previous slide, this part where you're adding a bond and you're getting a positive charge is similar to you're adding a bond and getting a positive charge. Or if you're removing a bond and generating a lone pair, negative. And in the case of nitrogen, you remove a bond and generate a lone pair, negative. So they're exactly analogous to one another. And I was basically explaining the little the part at the end of this where if you think of water, it's neutral. And if you think of your acids and base chemistry that we learned a long, long time ago, hydroxide's negative. Well, the oxygen's going to be bearing that negative formal charge because it's got 3 sets of lone pairs in one bond. Where hydronium, H3O plus, well, if we make 3 bonds, oxygen's only going to have 1 lone pair left, and it's going to have the positive charge. If you look at the course notes, I showed another sort of way of remembering this or calculating formal charge. I think it's slightly more complicated, but it might be something that resonates with you. So you can take a look at that. But what I thought I would do right now is return to our last Lewis structure and determine which one's better based upon formal charge. So we are going to share a new screen with, here we go. Share. Okay. So we were comparing these two structures to determine which one is a better Lewis structure. Now, one of the things that you might notice immediately is that this oxygen right here has got 1 bond and 3 electron lone pairs. So if we think of hydroxide, we're basically are going to know that this oxygen is going to have a formal charge of minus. Every other oxygen has got 2 bonds and 2 sets of lone pairs. So every other oxygen has a formal charge of 0. Now, what we don't know is about sulfur. So let's do some sulfur formal charges here because that is less common. Okay, so sulfur. So sulfur normally has got 6 valence electrons. It's right underneath oxygen. So let's look at the sulfur right here first. So our formal charge formula would equal 6 minus the number of bonds. 1, 2, 3, 4. Electron lone pairs minus 2, which will equal 0. So the sulfur in this molecule here has got no formal charge. In fact, the oxygens have no formal charge. So this structure has got no formal charge. What about this sulfur over here? Let's do it in a different color. Let's choose green. Okay. So formal charge equals 6, because that's what it has at the start, minus the number of bonds. 1, 2, 3. Minus the number of lone pairs. We got 2 electrons that are lone pairs. 2, this equals 1. So this would have a formal charge of plus. And it makes sense because this has got a formal charge of minus. So if we look at this structure here, we would have a plus on the sulfur. So when it comes to determining which is the best Lewis structure, and the best Lewis structure has got, you minimize the formal charge, then I would conclude that this structure over here on the right is the best Lewis structure. Okay, let's do one more example just for the sake of it. How about, let's draw BH4. pH4 minus. Let's do the Lewis structure and the formal charge on this. Okay, so boron has got typically 3 electrons. Hydrogens have 1 electron. There's 4 of them, so that equals 4. And we've got a negative charge here, negative charge. So this equals 1 electron. So our grand total is 8 electrons. Step 2 would be put the element with the highest bonding capacity in the middle. So, and this is typically the least electronegative. And if you look at the Pauling's, boron can make 3 bonds, hydrogens can only make 1. So boron has to be the center atom. We're going to connect these with bonds, the atoms in the periphery. And so that would be step 2. It turns out step 3 is already done because hydrogen can only have a duet. So 2, it's set. Each hydrogen's duet is complete. And in fact, the center atom's octet is complete. So we're all the way to the end. And we've got 2, 4, 6, 8 electrons. And this matches what we've got. Now, the one thing which we haven't done yet is the formal charge. And so what we're going to see, you can almost do this intuitively. The molecule's got a negative charge. So the formal charges in this Lewis structure, the grand total has to come out being negative. And so hydrogens can only make 1 bond, right? And we've got each hydrogen's only making 1 bond. So that means that boron must have the negative formal charge. And let's just do the math to confirm that it's true. So boron's valence formal charge. Okay. So normal number of electrons is 3, and you've got 4 bonds. So this equals -1. So our Lewis structure would be this. And you might say oh, wait a second, there's something, I can actually make this a better Lewis structure, and we're going to talk about that in the next section. And that's when we're talking about VSEPR theory and molecular geometry. Because the way I've drawn this might look like it's a planar molecule, but it's not. But we will do that in the next section.